Now that we have started the process of learning how to take an integral and how to do definite integrals, and we need to learn some more techniques because all we have is what's on that chart at the moment. But we need to start looking at recognizing patterns so that we can then work with integrals. Change of variables, general power rule, then do the same thing with definite integrals and involve doing integration. Now, the first key to doing other than basic integration is to work with a technique called U substitution, which involves learning to recognize patterns. Learning to recognize patterns as we look at these. We're going to call it U substitution. Because we are going to look at our integral and say, all right, can I do this by the rules that I have, the formulas that I have? Can I rewrite it? And if I can't, then can I recognize a pattern so that I can look at this thing called U substitution? Now, we're talking about trying now to take a antiderivative, trying to take an indefinite integral of a composite function. Composite function. And so a composite function is when we have a function called f, and we have a second function whose value is in the domain of f, and f works on g of x. That is our pattern. That is our way of writing a composite function. Well, in order to do the derivative of this, or the integral of this, we have to have it's the derivative of g of x there. So when I'm looking at an integral, do I recognize something here that will help me evaluate that? So we've got an inside function and an outside function. Okay? And so like the square root of a quantity. The outside function would be square root, the quantity is the inside function. Okay? In order to be able to find the antiderivative, I need to have the derivative of g of x inside this integrand. So we have to have all of that there in order to try and do the integration. In order to try and do the integration. And so it's recognizing patterns. Here we have the integral of x squared plus 1, the quantity squared, 2x dx. Okay? Now, when we are looking at an idea of a U substitution kind of a concept, and we're going to do this two ways, and it's the second way that I think is the easier, where we change the variables. But we've got this composite function, x squared plus 1 squared. That's the bigger piece, composite function. Then we have this 2x dx. And the key is recognizing that 2x is the derivative of x squared. So this 2x hanging in here is telling me, hey, look around for an x squared. So if our inside function is x squared plus 1, it's the inside function, then the derivative of that is 2x. And so I now have x squared plus 1 quantity squared, and I have g of x dx. I have the derivative of the inside function. Okay? And so this is just a power. Power rule says x squared plus 1 raised to the power, divide by that number, plus c. If you take the derivative of this, you'll get back to here. Now, I think this is easier done with changing the variables rather than trying to look at what's there, but try to change the variable. Okay? But try to change the variable. Okay? Do this one first. Okay? See this x squared plus 1 squared. Okay, that's our big function. That's the composite function. And then we have this extra x. And though I don't have the 2 with it, when I see this extra x, that extra x says, that has something to do with the derivative of x squared. And if I start to recognize the patterns, then I can do the result. U substitution. U substitution is what we want to try to do. We're going to identify that inside function. Identify that inside function. And let that be u. Then du is the derivative of that. And then by substituting, we can come up with it. There's a couple of videos on this also to go look at. And I'll do a couple of pencasts on this. But notice I want the integral of the square root of 2x minus 1 dx. Now, I know how to take the integral of the square root of x dx. But this is more than, this is a composite function. And the square root's not my problem, it's the inside. So let u be the inside, 2x minus 1. Then calculate the derivative of that. So du would equal the derivative of this, 2 dx. So now we have the square root of 2x minus 1. I can now write as the square root of u, because 2x minus 1 is u. And then dx, since I now know that du equals 2 dx, this dx can be substituted with du over 2. And now I rewrite 1/2 u to the 1/2 du, u du, power rule, so that's u to the 3/2 over 3/2. So 1/2 times 2/3 gives me 1/3 u to the 3/2 plus c. And now I resubstitute, because the question was, what is the integral of the square root of 2x minus 1 dx? Not what was the integral of something with u. The u allowed me to use the rules, so I resubstitute 1/3 2x minus 1 to the 3/2 power plus c. Similar problem, but again, I can't do this. I don't have any rule for x times the square root of 2x minus 1 dx. So when you're using u substitution, almost always, you look at what's the worst part of it. The worst part is this thing under the square root. So let u be the thing under the square root. Then du, we've already done that, du would be 2 dx. So dx is du over 2. So in place of the square root of 2x minus 1, I'm going to substitute in u to the 1/2. In place of dx, substituting du over 2. I still have this x. So I got to go back and see, do I have any relationship between x and u? And yeah, that equation. I can solve that for x. So u is 2x minus 1. X is u plus 1 over 2. So I substitute in for x, u plus 1 over 2. Now I have eliminated all the x's. And I've got a 2 in the denominator, another 2 in the denominator, so that's a 1/4. I have u plus 1 times u to the 1/2 power, so distribute. U times u to the 1/2 is u to the 3/2. U times 1 is u to the 1/2 du. And I can now do this integral. It's 1/4. U add 1, 5/2 over 5/2, plus u add 1, 3/2 over 3/2. So 5/2 times 1/4 gives me 1/10. And 3/2 times 1/4 gives me 1/6. U, I'm going to resubstitute. U is 2x minus 1. So 2x minus 1 to the 5/2, and 2x minus 1 to the 3/2, and don't forget our plus c. And we have evaluated using u substitution. U substitution. And so u substitution. So the general power rule then is, since I have a power rule, We've got the power rule. We just used it a couple of times. The general power rule, if it's g of x to the n, that composite function, g prime dx, that would be g to the x n plus 1 over n plus 1 plus c. Equivalently, we let u be g to the x. This becomes u to the n du, so u to the n plus 1 over n plus 1 plus c. As long as n isn't minus 1. We'll pick up when n is minus 1 another section or two down the line. So u substitution. So here's a problem. Here's the composite function. So if we let u be 3x minus 1, so u is going to be 3x minus 1. So this would be u to the fourth. The derivative of 3x minus 1 is 3 dx. So this just becomes u to the fourth du, which is u to the fifth over 5. U is 3x minus 1, so we substitute it in. We'll look through some of those examples. We'll do a few more examples to see that in a little bit. But that's called u substitution. Changing the variable so that something pretty ugly, like this one, we can do, because again, integrals can't be done except by matching. So now you have a definite integral from 1 to 5 of x over the square root of 2x minus 1 dx. Messy, right? Messy, right? So since it's messy, I want to rewrite it in terms of u substitution, right? In terms of u substitution. Now there's a couple of ways to get there, right? Right? They give us a couple of ways to get there, but here's one. The problem is my denominator. So if I let u be my denominator, then u squared would be 2x minus 1. So u squared plus 1 would be 2x. So u squared plus 1 over 2 would equal x. And if we look then this in place of x, I can put u squared plus 1 over 2. In place of the square root of 2x minus 1, I can put u. If you take the derivative of this, du would be 1/2 2x minus 1 to the minus 1/2 times, and then 2, doing the derivative, dx, and we can find out that u du equals dx. Okay? So it's pretty fairly easy from right here. It's easier actually. U squared would be 2u du. Derivative of this would be 2 dx. So 2u du would equal 2x, 2 dx, so dx would equal u du. Now we substitute, we rewrite 1/2. This would be u and 1 over u, so we're left with u squared plus 1. Now, the other thing is that 1 to 5 was x variables. But we're now in u. We're now in u. So if we let x be 1, u was 2x minus 1. So 2 times 1 minus 1. The lower index, changing it to 1. And 2 times the upper index, which was 5, 10 minus 1. Square root of 9 gives me 3. So we've changed everything to u. dx is now du. The x's, all of them are in terms of u. And the indexes are now in terms of u. I can't use 1 and 5 because 1 and 5 are related to x. So I have to rewrite and becomes 1 and 3. And now I can do this 1/2 u cubed over 3 plus u from 1 to 3. Substitute in 3, 1/2, 3 cubed over 3, that's 9 plus 3 minus 1/3 minus 1, and we get 16 thirds. We get 16 thirds. That's using U substitution. It's using U substitution. One last thing in this section is that if you have a function integrated from minus a to a, if the function is an even function, okay, if the function is an even function means it's symmetric around the y-axis. Therefore, this piece and this piece are the same, this and this. So if it's an even function from minus a to a, then that's the same as 2 times the function from 0 to a. It's go from 0 to a, find that area, and double it. If the function is odd, that means it's symmetric through the origin. And if we go from minus a to a, right, notice this area and this region, okay, but all the y values here are positive and all the y values here are negative, so these will cancel each other out. And so if f is an odd function, then from minus a to a of f of x dx always equals 0. So that's how we can find integrals, even if I have a little problem doing them from a geometric point of view. The integral from minus pi over 2 to pi over 2. So as soon as I see it going from a to minus a to a, same values, plus and minus, should look for one of these. Okay? Is this function sine cubed x cosine x plus sine of x cosine of x, is it an odd or an even function? Well, the way we figured that out was we substitute in place of x, we put the opposite of x. So sine cubed of minus x, cosine of minus x, sine of minus x, cosine of minus x. The sine of minus x, the sine is an odd function, back from trig. So that's minus the sine. So minus the sine cubed gives me minus the sine cubed. Cosine's an even function. Cosine of a negative is just the cosine. Sine an odd function gives me minus sine, cosine even function. And so I end up with minus sine cubed cosine x minus sine x cosine x, the exact opposite of what our original function was. That's the definition for being odd. Therefore, this integral from minus pi over 2 to pi over 2 of this odd function has to be 0 because of the theorem. Now this can be done, and I will, on a pencast, I will do this problem by hand, and then we'll demonstrate that it is that. But U substitution, one of the most important things as far as the integrals go. For going into Calc 2, this is the key, because the emphasis in Calc 2 is going to be integration. And when we integrate, we're going to learn some techniques. And right now you have 2 of them, basic rule and U substitution. But all techniques in integration go back to the basic rules. U substitution, we're substituting so that we end up with a basic rule that we can work with. And so spend some time working on the problems in section 5.5, one of the most important sections in Calc 1 up to now. Spend some time with it.